Families of random variables which are functions of say time are known as random process or stochastic process or random functions. Consider some examples. Suppose xn is the outcome of nth row where n is greater than or equal to 1, then sequence xn n greater than or equal to 1 is a family of random variables such that for a distinct value of n is equal to 1, 2, 3, etc., one gets a distinct random variable xn, where xn n greater than or equal to 1 constitutes a stochastic process known as Bernoulli process. Also, suppose that xn is the number of successes in first nth rows for a distinct values of n, which is 1, 2, 3, etc., we get distinct binomial random variable xn, where xn n greater than or equal to 1, which gives a family of random variables, is a stochastic process. Another one is suppose that xn, which is the maximum number of showed in first nth rows, then xn n greater than or equal to 1 constitutes a stochastic process. Another one is consider a random event occurring in time such as number of telephone calls received at a switchboard. Suppose that xt is the random variable which represents the number of incoming calls in an interval 0 to t of duration. Say 1 unit of time is a random variable x of 1 and the family x of t element of capital T constitutes a stochastic process where t is ranging from 0 to infinity. So, the set of possible values of a single random variable xn of a stochastic process xn n greater than or equal to 1 is known as its state space. The state space is discrete if it contains a finite or innumerable infinity of points, or otherwise it is continuous. One-dimensional process can be classified in general to the following types of process. One is discrete time, discrete state space. Another one is discrete time, continuous state space. Then continuous time, discrete state space. And continuous time, continuous state space. We consider process with independent increments. If for all t1, t2, etc. to tn, where t1 less than, t2 less than, etc. to tn be the random variables, then xt2 minus xt1, same way xt3 minus xt2, etc. to xpn minus 1 are independent, then sequence xt t element of capital T is said to be a process with independent increments. We consider Markov process. If xt t element of capital T is a stochastic process such that given the value of x of s, the value of x of t where t is greater than s do not depend upon the value of x of u where u is less than s, then the process is said to be a Markov process. The definition of such process is given below. If for t1, t2, etc. to tn, where t1 less than, t2 less than, etc. to tn less than t, then probability of a less than or equal to x of t less than or equal to b, given that xp1 is equal to x1, etc. to xpn is equal to xn, which is equal to probability of a less than or equal to x of t less than or equal to b given x of tn is equal to xn. Then the process xt, t element of capital T is a Markov process.